Hi everyone, welcome. I am Deniz Orta and a student from Istanbul Technical University, and I am one of your hosts today. First of all, thank you all for joining this event, sixth virtual student conference, which is organized by Society of Exploration Geophysicists Europe Region Advisory Committee. Also, it is nice to see everyone here. Also, it is amazing that all of us come together in this event across the world. Today, we will witness young scientists explain themselves and share their research. We have 8 students who is going to make a presentation from various universities. This conference consists of 3 different sessions, which is seismic applications and signal processing, hydrogeophysics, and case studies. Presentations will be 10 minutes and afterwards 5 minutes of questions. If you have questions, you can either type on the Q&A section in Zoom or raise your hand. Also, I would like to mention that this event being recorded and will be shared on the SEG website and YouTube channel later. Now I am giving the word to the chairs of the first session.
Good afternoon, everyone. This is the first session of the afternoon. This is called Seismic Applications and Signal Processing. So we are going to share the session. My name is Tatiana, and then we have here Emmanuel. So the first talk is Marty Faber from University of Edinburgh.
Okay, hello and welcome everyone to my presentation. My name is Mart and I'm a second-year PhD student at the University of Edinburgh, and I'm going to talk about imaging the near-surface zone with seismic wave-field gradometry. So I'll jump right into the motivation behind my project to set it into context. We would like to better characterize the complex near-surface zone, and more specifically, the so-called critical zone in which life, atmosphere, and oceans interact with the subsurface directly. This zone reaches from the tree line down to aquifer level and provides very important resources for modern life. But for this area of interest, it is not yet possible with standard already existing geophysical tools to map the highly dynamic processes that are going on in the shallow subsurface. So that is why we are trying to gain a better understanding via wave-field gradometry. So why do you think gradometry could be beneficial to this task? First of all, gradometry is sensitive to the physical properties of the near subsurface. Typically, we expect it to be able to image subsurface properties accurately in the upper 300 meters. It is also a passive imaging method, so it is non-invasive to the ecosystem and depends on ambient seismic noise recordings only. And most importantly, gradometry has very short recording times at the order of 15 minutes and allows to monitor the subsurface in almost near real time after data collection. So this might enable us to pick up and monitor processes that could not have been imaged in such a detail before. So if we want to characterize an area of interest, we usually start out in the field where we record wave-field data. So now we have these 15 minutes of ambient noise recording that contain all kinds of wave types and interfering wave-field energy. So the question is, how do we get information out of it if we not intend to cross-correlate traces, as is done in interferometry, for example? So gradometry as a method is defined by its underlying wave equation that is chosen to define analyzed wave field or the measured wave field. Then we calculate gradients of the wave field, as the name already suggests, that are directly related to the subsurface parameters. And as we are dealing with ambient noise here, we can make the assumption that our wave field is dominated by surface waves, whose propagation is can be described by the above 2D Helmholtz wave equation. So in the following slides, I will explain the concept of so-called 2D surface wave gradometry, which is based on this 2D Helmholtz wave equation. In this equation, the spatial wave-field gradients are related to the temporal gradients by the phase velocity, which we want to recover. But when we are in the field, we can't measure those respective gradients directly. We can only measure the wave field itself. So the idea is to compute the gradients discretely from a recorded wave field. Yeah, and we are going to do this gradient calculation over a whole grid as it relates back to the field example I just showed. And the method we use is finite differences, which allows us to approximate the second order derivative, so the wave field gradient, at a central point marked here in green, through having information about wave field quantity itself at 4 neighboring stations. So having calculated those gradient values discretely, we can then plug them into the wave equation. And as we can see, both the spatial gradient and temporal gradients are related by a scaling factor only. So if we plot them against each other, we receive a linear trend. And the slope of this line represents the phase velocity at one specific receiver station, which can then simply be recovered by a linear regression. If we take a look at a different receiver station, slope changes if the velocity changes. And following that principle, we can construct phase velocity maps over a whole receiver grid. And if we then do that for each filtered frequency, we can construct local dispersion curves for each receiver station, which gives us then 3D information about the subsurface. And the quality of those obtained images depends on how well the used wave equation, so how well the 2D scalar Helmholtz wave equation approximated the measured wave field. So to make sure that those images we obtain are as accurate as possible, we need to take a closer look at the wave equations we use for grid geometry. And this leads me to the aim of my PhD project, where we want to introduce more sophisticated and physically representative wave equations into the 2D grid geometry workflow. So traditional wave equation that is used is the Helmholtz wave equation, which makes quite a drastic approximation on how waves travel in the subsurface. So depending on the recorded wave field, this might be detrimental to the quality of our phase velocity estimates. So this is why we would like to introduce a new wave equation into the workflow, notably the full acoustic wave equation, where we consider density to be a variable and not only a constant as is assumed in the Helmholtz model. So if we visually compare those two equations, they are very similar. And we see that we can get phase velocity out of both of those equations. Now the question is if we can additionally estimate density from this full acoustic wave equation. And in order to test this, we set up a synthetic modeling study. So to start out, we use a 2D acoustic forward modeling example, because this ensures that we are not subject to any kind of approximation effects, because the underlying wave equation that we use for grid geometry represents the physics behind the synthetically produced wave field accurately. So both velocity and density models are smoothly varying in space with different heterogeneity scales, and they differ in their orientation. So the choice of this velocity density model choice might appear quite unphysical, as those two quantities are usually interdependent. But we chose this extreme model on purpose, as it allows us to be sure that what we recover is actually the density response and not some type of artifact from the much stronger velocity signal. So it's kind of a proof of concept. So in terms of source setup, we place 10 ring sources around our receiver grid, each fired at different times and with different source signatures over a large frequency spectrum in order to simulate ambient seismic noise. And the synthetic wave field is recorded at a receiver grid in the middle. So in the first instance, I tried to define the magnitude of the density signal that we want to invert for. So I calculated the spatial gradients from the true known model, both for the traditional case, where density is assumed constant, which is plotted here in as the blue line, for the case where the gradients are influenced by the density. And this is indicated here in dotted orange. And when we plot the difference between those two discrete gradients, we can see that the density signature is quite small, but well detectable. And if we now analyze the effect of this density signal onto our velocity estimates, we can clearly see effects of the density model is neglected here in the Helmholtz model. And if we compare it to the velocity that we recover with the full acoustic model, we can observe that it performs quite a bit better and that it looks very similar to the true inputted velocity model. So this improved accuracy of the velocity estimate through giving it density information motivated us to set up the inverse problem with this more realistic full acoustic wave equation. So that's what I did. I set up a linear inverse problem via least squares minimization. And I showed the parameterization of the system here on the top right corner. But due to time constraints, I don't have time to go into it in detail. So you just have to believe me, I guess, if I say that we have an unknown in our data vector, and we need an initial guess to kick off the inversion. And as an initial guess for the density, I chose homogeneous constant one in order not to bias the system towards any structural heterogeneity. And as an initial velocity guess, I took the output from the traditional Helmholtz wave equation inversion. So we do not have any density information yet. Then we invert for our parameter G, which contains our density information following the least squares minimization expression of the problem. And this gives us a first estimate of the density, where we can already see that general structural trends are quite well recognized, but there's still a lot of room for improvement. So we want to update our initial guess of this parameter. And as input for this updated parameter, we choose the recovered density from our first inversion iteration. And then we update the velocity with the full acoustic wave equation. And it becomes already noticeable how the velocity estimate improves with the given density information. And this then allows us to update or to conduct a second inversion iteration, which already shows improvement of the root mean square error and also has more clearly emerging heterogeneities. And then we update as many times until we are satisfied with our density output. So here I show the evolution of the root mean square error over the number of iterations. And already after 17 iterations, we can see that we approximate our minimum expected error. So after 17 iterations, we are happy with the results. That gives us a recovered density model that is comparable to the true model. Similarly, this is the case for the final velocity estimates, where we could reduce the root mean square error by about 80% through feeding it this density information. As a summary, we are able to recover the relative density structure with the proposed full acoustic formulation of gradometry, and we are able to improve our phase velocity estimates. And in this talk, I only showed the example for the 2D acoustic models, but I also have conducted some tests for both 3D elastic and viscoelastic models, which suggests that density is also recoverable in a more real Earth model. So yeah, with that, I would like to finish my presentation and thank you for your attention.
Okay, thank you so much for this interesting and very good presentation that we have seen now. So we open now to some questions. If the audience has some questions, please write it in the chat. So for now, I can start with some questions. So did you use theoretical data, right?
Synthetic data, yes.
synthetic data. Do you have the opportunity to use this method in real data?
Yes, that's what we are hoping to do in a field session in the coming fall. So we want to deploy our receiver stations over an abandoned coal mine that is used for geothermal energy. And we want to show that we can characterize this cavity kind of with our method. And then we also want to show that these theoretical extensions that I just showed, that they are also possible in the field.
Okay, good. So I guess this is for next work.
Yeah, so this is basically proof of concept synthetically, and then we hope that it will be possible in the field. But this method has been used with the standard Helmholtz equation formulation. It has been used in the field and shown to produce very good results.
Okay, good, nice. So during your study, during this process, which limitations do you encounter when applying this method?
So I think, if we record ambient noise, we don't really know what kind of frequency content we get. And we do want to produce dispersion curves. So we kind of hope to have we call it a broad frequency spectrum, but this is of course not always the case depending on where you record. So this could be a limitation, that we have kind of sparse, reliable frequency information. And that we basically only have don't have such a good 3D image, just like a few 2D information basically.
So I have one last question from my side, and it's like, do you have other options, other methods, or how did you choose this method for develop your work?
So I guess in the future of gradometry, the gradometry has been compared already to interferometry outputs. So they had a data set over the Ecofisk oil field, and then they compared phase velocity maps from gradometry and interferometry, and they produced very similar results with the thing that gradometry can produce results in only like a few minutes of recordings, whereas for interferometry you need several hours of cross correlations. But interferometry still produced more accurate results. So for the future of gradometry, we still need to compare those two methods and see how to improve the propositions that we make, how they improve the results of our method.
Well, we have one question here in the chat, and it is, do you expect this to work on the sea floor with nodes?
Yeah, so that's the example so that was what they did on the Ecofisk oil field. They had kind of an ocean bottom array. So they had their receivers at the ocean bottom and could produce very good phase velocity maps.
Okay, thank you so much for this presentation. So now I want to introduce the next one. So we want to introduce Cinta Nur Asidad from Universitas Pertamina. So now the floor is yours, and now you can start presenting.
Okay, good afternoon, ladies and gentlemen. I would like to say thank you for coming to my presentation. It's great to see you all. My name is Cinta. I'm from Geophysical Engineering Department at Universitas Pertamina. In this opportunity, I would like to present research by my team, Cinta Nur Asidad, Sandi Suharja, Indra Siregar, Cyrillus Begarian, Cecilia Putri, and Muhammad Ramdan, entitled Local Seaway Splitting in Merapi, Merbabu. This is the outline of the presentation. Without wasting much time, I'll start with the background. As we know, Central Java are part of Sunda Arch, which has relatively high seismicity and a complex geological system due to the Indo-Australian plate that is subducted under the Eurasian plate. The convergence rate varies from 5.6 centimeter per year in the western part of Java to 6.5 centimeter per year in the east. When the subduction zone is very active, the material that enter the Earth will slowly move toward the continental crust. This caused the angle of subduction to become more slanted and the part of subduction to change as if it is moving, creating a new volcano south of Mount Merbabu called Mount Merapi. Until now, Mount Merbabu has been an inactive mountain because it is an old volcano on the island of Java. Meanwhile, Mount Merapi is one of the most active volcanoes in the world. Seismic anisotropy has been widely studied to reveal the geodynamics and deformation occurring within a subduction zone. One common method to study seismic anisotropy is shear wave splitting analysis. Modeling, interpreting, and analyzing the result of local shear splitting in Merapi-Merbabu area were the goals of this research. Previous research by Kolakov et al. Regarding tomography in Merapi area state that low velocity anomaly indicated by the yellow color, which corresponds to the seismic area and reflect the flat part of the shaft. Based on research by Suharja, using the reservoir function method, it is stated that the depth of the Moho discontinuity under the area in Merapi-Merbabu under Merapi is about 30 kilometers, and it is getting shallower on the west side of the station. In addition, the research by Ramdan states that high VPVS ratio under Mount Merapi, while Mount Merbabu is dominated low VPVS ratio, confirm that Merbabu Mount is much less active than Merapi. Confirm that Merbabu is much less active than Merapi. And the research by Gerardo Leon on shear wave splitting in Rivera Coco subduction zone explained that the SWS method result use a teleseismic event fast direction that are approximately perpendicular to the Middle American trends. Meanwhile, shear wave splitting result from local events show mostly parallel to the trends. This research is located in Merapi-Merbabu area with the following coordinate boundaries. The data used come from local earthquake catalog and with three components: space and recorder data from the Irish earthquake catalog in the period spanning from October 2013 until December 2015 with a total of 33 stations. And the minimum magnitude used is 5. And figure 1 show a map of the distribution of station in research area. In processing, we use Python programming language, and the download data is sourced from Iris, and the pre-processing in the form of filtering is carried out to obtain better signal quality. In these studies, detrend and bandpass filter are used with a range of 0.5 until 1. In addition, the arrival time of the S wave was chosen to show that local earthquake event could be more visible. The next steps in the SWS method is to automatically calculate the eigenvalue, which is in accordance with the calculation of Silver and Chan 1991 as shown on the right side. Okay, and the result of the processing SWS method is back azimuth parameter, which is shown the direction of polarization and delay time. The following is an example of raw data, namely ME20 station with an event on November 2013 with a span of about 3 minutes. And figure 11 shows the result of processing sample data after trimming, detrend, and filtering. In the result of S wave splitting shown in the figure, there are several events. The waveform cross-section of the wave shown the difference in arrival time of the north and east wave. The two waves arrive in approximately 50 seconds as shown by the green line. However, it can be seen that the north wave arrived first, followed by the east wave just 1 second later. The four squares in the middle are split result for wave bounded by black line on the full waveform. This different calculation will result in different movement. Before calculating the eigenvalue, this method corrects the data as well as rotate the seismogram. This correction is carried out with the aim of changing the north-south and west-east component to radial and transverse component. So the zero vertical and the zero horizontal energy can be seen more dominantly in each seismogram component. Okay, and this correction can be seen in 4 boxes on the left in the figure 12, where the 2 boxes above are before correction and the box below are the result of the correction. The transverse and the transwave, which is indicated by orange color, will have a value that tend to be stable and flat. The result of the correction are considered correct if we look at the motion of the seismogram particle, which were initially relatively elliptical but have become more linear. The bar on the right depicts the topography of calculation of minimum eigenvalue, which shows the direction of polarization, which is the polarization is -70 plus minus 7.50, and the delay time is 0.76 plus minus 0.06 seconds. Okay, the result of the zero wave splitting method processing are back azimuth parameter, which indicate the direction of polarization and delay time as shown as in the following table. N is the number of event, and back azimuth and delay time value are the average value of the event used at each station. And the aim of the research is to interpret and analyze the result of parameter obtained in the form of fast direction polarization and time delay by correlating geological feature and previous research at the research location. We can see in figure 13 that there are 2 anomalies in zone of interest that are shown by different pattern around the Merapi and Merbabu area. The black line shows the average of polarization direction, and length of their length is proportional to delay time. In general, the direction of rapid anisotropy polarization in Merapi Merbabu area has a different rotation pattern and its station, and this is most likely influenced by difference in age and direction of absolute plate movement in Java. In Mon Merbabu area, the direction of polarization is relatively southwest-northeast oriented, which is perpendicular to the trends. In addition, interestingly, we can see that the direction of back azimuth corresponds to the direction of subduction plate on the south coast of Java. The average delay time in Mon Merbabu area is 0.5 seconds. Meanwhile, in the Mount Merapi, the direction of polarization tends to be more random or not perpendicular to the direction of the trends, with the delay time value tending to be greater than in Mount Merbabu area, which is an average of 0.08 seconds. So it should be suspected that from the 2 anomalies, there are differences in subsurface structure. Okay, from this discussion, we can conclude that first, local zero splitting modeling in Merapi Merbabu are successfully carried out with the filter use from 0.5 until 1 meters. And second, there is a difference in pattern on back azimuth and delay time value in study area, which is indicated by difference in both tectonic and lithological layer in the area. In the Mount Merbabu area, the direction of polarization is southwest northeast oriented, Meanwhile, Mount Merapi show most weak or overlying crystal anisotropy with a phase direction that is parallel to the threads. Okay, that's all from my presentation. Thank you very much for your great attention. It is hoped that this research will allow for a deeper understanding of the geodynamic of Merapi and Merbabu. I'm Sinan Rashida, and good afternoon.
Thank you so much for the presentation. Now we open this time for some questions. If anyone in the audience has some questions, you can write it in the chat. Okay, meanwhile, I can ask something. Were the results validated using any other methods in the area, like borehole data?
For validating my research, I use some literature, some previous research, such as in Sandi Suharja research. There is two anomaly in tomography, and that in Merapi has a low anomaly, and in Merbabu has a high anomaly. So I think this is can become the addition of to validate my research.
Okay, thank you so much. So we don't have questions in the chat, so then we can proceed to the next talk. The next talk is Lucas Nienemann from Institute of Geophysics and Geoinformatics from Freiberg. Lucas, welcome to this conference. So now you can start sharing your screen and presenting.
So now comes the signal processing part we talked about, and my title is Efficient Detection of Complex Spikes Using the Haar Wavelet Transform and Bayesian Statistics. And it can sound quite intimidating, this title, so I added some colors to make it look nicer, and they are related to my structure. First, I'm going to tell you something about what these complex spikes actually are, then a bit what a wavelet transform is, and then my main part, the Bayesian statistics, and last but not least, something about the efficiency of my algorithm. But first, the complex spikes. And now we have to look at the data those spikes are actually in, and those are accelerometer data, so sensors that measure acceleration. And you can see here on the left, typical data of that. They reach from gravity to minus gravity, so they measure the gravity too. And you can see some waves there very faintly. And of course, the big spike trail we want to detect here in about 1 second time. And on the right, you can see some example of a very scary big spike we like to detect. But they're not always that big. They're also sometimes small and comparable to waves, as you can see in this picture, but they're always caused by a sensor reset, and they have variable duration and amplitude. They always go in the direction of zero acceleration, and they have a strong high frequency component, as spikes used to do. And they are incoherent between traces. So we like to detect something that fits this description. And we start with a wavelet transform. And a wavelet transform is a successive decomposition of a signal into approximations and details on different scales of resolution using Haar wavelets. And there's no loss of information involved. That means it's invertible. And there are a lot of wavelets, and I chose the Haar wavelet because it's the most spike-like of all wavelets, and that's good to detect spikes. And now, why is it useful? We can use this Haar transform on the actual accelerometer data. As you can see here, we can decompose the original shot into an approximation and a detail. And yeah, the approximation looks almost like the original, but it's different. And the detail scale is centered around 0, and those complex spikes are outliers in the detail coefficients of high scales, which is what we wanted. And now already to the Bayesian statistics part. First, what's that? Bayesian statistics is a system for describing uncertainty using the mathematical language of probability, which is a nice definition, but what does it actually mean? For that, we can look at some example here. We drew some data from a normal distribution, and now we want to evaluate or estimate the standard deviation this distribution had, and we use the normal formula down there and come to an estimate of 3.3. But since we actually synthetically modeled those data, we know that the normal distribution we drew the data from has a standard deviation of 3.75. So does that say the formula is wrong? Fortunately not, but the formula doesn't know anything about uncertainty, and the Bayesian statistics can do that better and give us an estimate of this standard deviation as a probability distribution and tell us something about the uncertainty involved in this estimate. And now we come to our problem, and first, what's an outlier? Good question. And for that, we have to look at the coefficients here on the left and define some localization, some neighborhood, as we can see in this square thing there. That's my neighborhood. And I say that all the coefficients are essentially comparable in this neighborhood. And on the right, we can see a histogram of that neighborhood with these wave coefficients in green and the spike coefficients in red. And we clearly can see that the spike coefficients are indeed outliers. And this has got some physical reasons, or that waves are very unlikely to produce coefficients not fitting their neighborhood because they are coherent and band limited. And the spikes do that, they produce unlikely stuff for their neighborhood. So what's unlikely? Bayesian statistics says unlikely is what's got a low predictive probability. And predictive probability is the conditional probability of a wavelet at the center of the neighborhood given the surrounding coefficients. So we got this 9 times 9 coefficient neighborhood, and this center is the coefficient we want to know if it's unlikely or not. So how to get that probability? First, for that, in Bayesian statistics, we always have to define a statistical model. And for that, we here assume that those coefficients are normally distributed. And this assumption, or in truth, they are not, but this assumption can nevertheless be taken since the waves are actually less likely than a normal distribution to produce outliers, which is a very nice property of them. And waves also have the nice property that their mean is 0. So our statistical model is for the coefficients in a neighborhood is a normal distribution with 0 mean and unknown standard deviation. Now we can calculate the predictive distribution analytically. And if we do that, the result is a so-called t-distribution. And this has two parameters, the nu, which is the number of coefficients in a neighborhood, and the sigma squared, which is the variance of the neighborhood. And on the right, you can see the t-distribution compared to a normal distribution. And all this plot says is that if you ask a normal distribution, everything's an outlier, or it's much more likely that if you use a normal distribution that something will be declared an outlier. And if you use a t-distribution, this is less likely the case, and it can handle the uncertainty better because it has this parameter nu, which is the number of observations we actually have to base our reasoning on. So if we have just one observation, we are very unsure about what's an outlier and what's not. But if we have 100, we're pretty sure. Now, next step, the third step, is to formulate our prior beliefs in the form of a prior distribution. And our prior belief in this case is that some traces have a higher noise background level than other traces. And we can give the distribution, we can give the information to it. And what we get afterwards is the picture on the right with some not outlier probability, just using the assumption that the noise level is different for different traces. Now we want to make this probability distribution better, and we're doing this by calculating something called the posterior hyperparameters. That's the parameters of this t distribution. And for that, we start with the coefficients and on the left, and we first exclude everything that might be a spike. We're suspicious of it. We exclude it from our evidence, and then we compute those hyperparameters for every neighborhood. As you can see on the right, the number of evidence in a neighborhood and the variance of that neighborhood. And now we can evaluate this t distribution with our calculated parameters. As you can see, we start here on the left with the coefficients again, then our known prior probability, and then the posterior probability, which incorporates the data of the neighborhood. So we have more information, and we can see that from the prior probability to the posterior, our estimates have gotten better, since there are in this region here, there are some waves with a high outlier probability comparable to the spikes. And in our posterior probability, the spikes have very, very low not outlier probabilities. So we are very sure that they are outliers compared to the waves, where we are very sure that they're not outliers. And now we can set every coefficient with a p-value of less than 10 to the power minus 10 to 0. And we do this for the 3 highest scales of our wavelet decomposition. And the next question is, how do we combine the results from these different scales? And we do this with the inverse Haar transform. And you can see here in the middle the inverse. And the inverse is almost everywhere the same as the original, just where we set some coefficients to 0, they're changed. And this change is indicative of a spike there. And if we look at the change that has the right sign, we can produce this very nice spike mask over there. And now, last but not least, the efficiency. Is it fast? And the wavelet transform is indeed very fast. It's got a linear time complexity, which means the computation time increases linearly with the problem size, which is better than the fast Fourier transform, for example. And the calculation of the hyperparameters can be done with like a fast summation algorithm called partial sum algorithm, also in linear time. And this means the whole algorithm can be done in linear time and is indeed very fast. So these times you see down here were with a Python implementation on my laptop. And they can be, they indicate that, for example, a shot with 90 million samples can be processed in under 10 seconds on my laptop, and on other machines it should be faster. And last question, is it good? And for that, we need to compare it to some other algorithms. The previous algorithm has some faults in the beginning, and because it's too clustered there for it, so it's not good. Then we have some example of the neural network I implemented. This one does detect every one of those big spikes, but has problems with small spikes. And the Bayesian algorithm is the only one who detects very small ones and very clustered ones as well. So now I would be happy to answer some questions of yours.
But even though we're running low on time, I would like to just throw this one question at you, and then we go on for our break. And the question is, you know, like maybe every other person here knows that the problem with Bayes statistics is how easily you can influence your results with your prior probability. How did you take care of this kind of problem in your own case?
Yeah, my prior probability, I didn't give it a lot of weight. So I used a more or less uninformative prior. So the weight of the data in my estimate is much higher than my prior probability, and the noise level is actually it's a good prior belief that if the noise level is high in some trace, then it's unlikely to be a spike, but just some noise that happens to be there.
So hello everyone, my name is Jonathan Eifeldijk and I would like to welcome you to the second session of today on hydrogeophysics. I will be chairing this session together with Anna, who is now welcome to introduce our first speaker of today.
Thank you, Jonah. So our first speaker for this session is Walter de Lier Snyder. He's from University of Leuven, and the presentation is about tuning the sharpness of hydrogeological inversion models. And the floor is yours. You can share your screen if you want.
Okay, thank you for that introduction. So yeah, I'm from the Ghent University and the KU Leuven from Belgium, and indeed my talk is going to be about tuning the sharpness of geophysical inversion models. And I will apply it on a specific case of Flanders salinization map. It is a map that shows the depth of the fresh saltwater interface, and you can see from this map that the saltwater is actually in the shallow subsurface from 5 to 10 meters below the surface. But the problem with the map, and that's something what I try to improve in my PhD project, is that it's overly smooth. And the fact that it's overly smooth can be problematic for the estimation of the depth of the interface. And the figure on the right tries to illustrate that. The dark blue line is an example of an overly smooth interpretation of the data, while the true expected transition between fresh and salt water should be relatively sharp, as the black line indicates. So a small difference in the definition of what should be the interface between fresh and salt water in electrical conductivity has a larger effect on the estimation of the depth when the inversion is too smooth. So that's what I tried to improve with this project. So the map was obtained with time domain airborne EM data. So a helicopter flew over the polders and emitted the transient magnetic field. And this is sensitive to the electrical conductivities. And on its turn, the electrical conductivities can be related to the salinity via petrophysical laws. So to go from the data to the actual image of the subsurface, we need to do some geophysical inversion, typically done with the minimization of an objective function. And the first term is a data misfit, typically a least squares misfit, which tells you how well a specific image is in agreement with the data that you have measured. But like most geophysical problems, it's a nil-post problem. So we can think of an infinite amount of Earth models, acceptable Earth models that can fit the data. So we need to add some regularization to the inversion. And in geophysics, that's typically an Occam's razor sense, which means that if you have two inversion models that fit the data equally well, then we should choose the inversion model that is actually simplest or exhibits the least amount of structure. And that's also the focus of this research for this specific part, where I need to develop a novel model misfit term, which is a little bit more flexible than the normal model misfit terms. So I want to add a specific parameter that will allow me to get either blocky, smooth, or in between inversion models. And the idea is to use wavelet theory. So we will decompose the inversion model in the wavelet domain, which is, in simple terms, basically decomposing an inversion model as a series of building blocks of the same shape, but with various widths and at different locations. And then we need to still translate Occam's principle into that framework. And that's what we do with selecting, okay, the idea of a minimum structure inversion model is a model that is built with the least number of building blocks. And in a formal setting of optimization, this is translated into a sparsity constraint. So this idea has actually already been applied to geophysical inversion, but we added the novelty that of scale dependency. When you look deeper into wavelet theory, it has some theoretical origin as well, but it's also quite intuitive. The scale dependency will assign a larger cost to small building blocks, as the small building blocks usually correspond to adding detail to the inversion model. So it makes sense that you have to pay a larger cost when you want to introduce a detail. Otherwise, you may overfit the data. So that's the idea. So let me illustrate the flexibility of the method on a toy model. So on the first row, you see a series of waveless basis functions. These are actually the building blocks that you can use to build one inversion model. The first one is actually the Haar wavelet, which we have already encountered in the previous talk of Lucas. And this will generate like spikes, or at least an inversion model with a very blocky nature. But the other wavelets have different characteristics, and you will see those characteristics in your end result, the final recovered model. And there is like a gradient from very sharp transitions to smoother transitions. For example, DBC6 on the right-hand side has smooth properties, so it will also result into a smooth recovered model. And that's also what we see when you look at the inversion models. The characteristics of the wavelets are most often present in the recovered model itself. And we get different realizations, recovered models that can fit the data equally well, but with different characteristics. Also good to know that this code is available on GitHub, so you can check it out there. It's made so that it can fit within the SIMPEC framework for people who sometimes work with SIMPEC, but there's also an example showing how you can use it with your own code for inversion. So it should be relatively clear. And if not, please reach out to me. But okay, let's go back to the actual salinization map. Let's look at a synthetic model. So on the left-hand side, we have a synthetic model where a highly conductive saltwater lens is lying on a clay layer with some fresh water on top. So we generate some synthetic data, and then we will invert the data. And then suppose we don't have any clue about what the inversion model should look like. We can then generate an ensemble of inversion models that fit the data to the same noise level. So on the right-hand side, I show 9 examples of inversion models that fit the data up to at least the noise level. And here I vary the wavelet basis function for each orientation. For example, and that's also the flexibility of the method. The first figure A, we use the blocky wavelet basis function along each orientation. And then, of course, you also get a blocky inversion model. But for example, in figure B, I changed the wavelet basis function along the horizontal orientation to DBC2, and then we get a different result with a more smooth but still sharp transition in the horizontal orientation. Figure G, on the other hand, uses a smooth wavelet basis function along the vertical orientation and a blocky wavelet basis function along the horizontal orientation. So when we look at some field data, this is the way how we can incorporate prior knowledge. So the data doesn't really have that kind of information, as we can generate all that kinds of inversion models and still fit the data up to the noise level. So we incorporate it and pose it actually with the choice of a wavelet basis function. And it would make sense in a salinization context to use a relatively sharp transition along the vertical orientation, for example, DBC3, and to use a relatively smooth transition in the horizontal orientation. And that's what we have done. And then we get an inversion model, which is at least acceptable. And it also fits the data. But we want to take it one step further and validate that result. And then luckily, I was awarded the Brill Marine Research ID grant, which will allow me to collect additional high-resolution data, high-ERT data, borehole loggings that will allow us to get a lot of information about the sharpness along the vertical orientation, and also ground-based time domain EM data. This ground-based methods allow us to have to get more reliable information on smaller scales, because remember the original data behind the salinization map is from airborne EM data, and this has a large cone of investigation, so the data contains information of relatively spread out a spread out image. So you have to really get that information from other methods to then impose it via the wavelet basis idea into our model. So we will do that in a specific calibration zone to get an idea about the sharpness along this orientation. We will then apply it to the salinization map, and then still as a validation step as a last step, which is available at all places of the region, but not really enough data to use that as a calibration step. So thank you for your attention. If there are any questions, I would be very happy to answer them.
Thank you very much for your presentation. We now open the floor to questions. If anyone wants to ask anything, just write on the chat. I have a question. You apply this to 2D profiles, right?
Yeah.
Can it be applied in a 3D volume?
Yeah. That's actually, I first published it for 1D, and then there was still some work that has to be done to do it to 2 dimensions, but it can now be easily extended to 3D as well.
Yeah.
And we plan also to make the code available for the 2 and 3D soon.
Yeah, and then you'll have 3 wavelets, one for each.
Then you can, of course, when you add the dimension, okay, you have much more availability, so we can vary much more and get much more inversion models, but still you need to make an educated guess on a wavelet that would make sense on that direction.
Okay. I have another question, if I can. Is that a good way to fit the wavelets to your data?
I'm not sure if I get that question.
So you used a theoretical wavelet to.
What we actually do is we try to incorporate the prior knowledge about the sharpness onto the inversion model. So we still let the data speak. We still use normal optimization models until we fit the data. But then still, because it's in build post and not unique, we can think of an infinite amount of inversion models that could fit the data. So actually this method allows you to easily incorporate that kind of prior knowledge. While, for example, when you have Tikhonov regularization, it will also always be smooth. And when you use sparsity-based method, it will always be blocky and sparse.
Yes, so sorry. I just needed to be very fast. I just wanted to know, I'm asking this question to Walter also. For someone who doesn't have an experience or who hasn't ventured into modeling and the likes, as a young geophysicist, what can you advise? How can you advise someone to start? How can you advise me to start so that I can be able to model and predict data sets as you do? Thank you.
Well, my advice would be to look out on the internet to already existing codes. For example, I mentioned the SIMPEC community, which has a lot of already existing codes for many geophysical applications, also including inversion components, and a lot of tutorials as well. And I think a tutorial-like approach of already existing code that is available would be the fastest route to learning all that kind of stuff.
Thank you very much.
Well, once again, thank you for your very interesting presentation. And I think we'll now have to move on, but you were perfectly in time, so thank you for that as well. So our next speaker will be Agha Adipta. I hope I didn't butcher your name as well, but I tend to be quite good at that. And from the University of Miskolc in Hungary. So the floor is yours.
Well, good afternoon, everyone. My name is Agha Adipta. I am a second-year master student in Petroleum Geoscience Engineering in University of Miskolc, Hungary. On this occasion, I would like to talk about my thesis, which is an application of Poisson impedance and length parameter extraction to discriminate the lithology and pore fluid detection. So this is the outline of my presentation. There is 6 outlines: introduction, methods, results, conclusion, acknowledgement, and reference. So to put into context, my research is a bit more into oil and gas exploration. So a brief description of my field is located on Drava subbasin in the Great Pannonian Basin, Hungary. So recently, it has been estimated that there is an undiscovered resource, P50, around 100 million barrels of oil, 1,000 billion cubic feet of gas, and 32 million barrels of natural liquefied gas. So despite of the recent tension on the eastern front of Europe, fossil fuel demand is inherently increasing. Despite that, Europe is also going towards the zero net carbon emission in 2050. So coming into the geological context of the Drava Basin, the Neogen rocks on the research location is a principal reservoir unix that consists of approximately 80% of reservoir on the region, and Lower Pannonian, which is known as the productive reservoir, which counts into a shallow water, fluvial deltaic, and lacustrine depositional environment. So in this case of the positional environment, we will expect to see some kind of shelly sands, a bit interbedded of shale and sands. So this kind of depositional context will be somehow be a challenge to discriminate and to characterize. So the main question is, how do we discriminate the lithology and pore fluids in shelly sands? So quantitative interpretation, or QI, on precise seismic inversion is one of the main industrial standards in the oil prospecting and reservoir characterization, within the goals of to know what is the lithology, how much the reservoir quality, and what is the pore fluid contained in the certain lithology. So quantitative interpretation primarily using the precise seismic inversion, which also commonly known as the simultaneous inversion, using the Fate approximation deriving from the Zuppe's equation, we can achieve this P-wave reflectivity, S-wave reflectivity, and also density. And incorporating these parameters, we can achieve the P impedance and Z impedance. Based on the obtained impedance, both of the impedance, we can distribute this and generating other attributes such as Poisson impedance, which is a attribute that that actually have a skew relationship between the P impedance and Z impedance. And the other is the lame parameter attribute, which is actually the idea is to extract the bulk modulus and also the shear modulus, where the bulk modulus is sensitive between fluids and matrix, and where the bulk modulus is more sensitive towards the matrix. So based on these two known parameters and distinctive characteristics, we try to utilize that to disseminate which lithology contain which fluids. So based on this basic idea, we try to derive it into the length parameter, which is lambda mu. Lambda is indirectly correlates with the incompressibility, and mu is indicates the rigidity. So based on the basic equation of VPVS, we can have this parameter of lambda nu and mu rho. So lambda nu rho is also is a very known approach to discriminate the fluid and lithology. It also has been established in a few cutoff as shown in this diagram. So on the workflow of our research is mainly based on two data set. The first is based on the well data set, where we delineate the data and transform the logs into P impedance, S impedance, Poisson impedance, and lambda nu rho, and we cross-plot it and delineate what is the pore fluid and what is the lithology. On the seismic approach, we running into the standard interpretation, angle stacking, seismic volatile, and then we'll going to this fault interpretation and horizontal interpretation, and then we will running through the inversion. After the inversion, we will have the inverted volume of P impedance and S impedance. And basically, we will run into the same transformation as the well data, which is getting the Poisson impedance and also the lambda nu rho. So based on this transform volumes, we will got the distribution of Poisson impedance, lambda nu, and lambda rho. So coming to the conventional full stack seismic section, we can see that the interpretation is consisting running through a anticline, and the bright spot we can see that it is inherently appearing on a few sections of the seismic. So if we are looking through the well data, we have calculated the petrophysical parameters and also transformed into the lambda nu rho and also the Poisson impedance and PS impedance. We can see that there are distinctive characteristics on the presence of fluids. We can see on this yellow scheme. So on this preliminary identification, we can see there is three actually promising intervals, but based on the previous production test, only SEN1 and SEN2 that actually have an actual presence of either gas or oil and gas. So we try to make a crossplot between these two data. So the left is the crossplot between P and S impedance. So on this data, we can see there is an indication of trend line of shale line and also the sun line. So the sun line is also, the color plot is also the petrophysical data. So we can actually know that the gas is actually saturated with the either gas or oil. So, but the greater discrimination is actually when we try to utilize the Poisson impedance, where the bigger separation is apparently seen on this shale line and also the other gas line. So using also the lambda nu rho, because we already have this so-called cutoff, we can discriminate which part of the the sand is actually saturated with gas, which one is saturated by oil, and also which one is actually considered as a low saturated oil or going towards a brine or water formations. On the inversion analysis, we can see that we try to incorporate the data, the well data towards the seismic data on the pre-stack seismic data. So we can see that the target is relatively thin, which is around below the tuning thickness. On this SAN 1, it's approximately 8 meters, where the tuning thickness is around 26. And it is expectedly more pronounced on the SAN 2 lines. So based on the inversion, we can see the comparative results between the P impedance, S impedance, lambda rho, mu rho, the RMS amplitude, and also the Poisson impedance. So we can see that based on the P impedance and also lambda rho and Poisson impedance, we can see there is some distinctive low impedance on the flank of the anticline. So this is a general indicative of the hydrocarbon presence. On the SAN 2 line, map, we can see that actually the anomaly, the low impedance anomaly, is following some kind of meandering fluid field geometry, which is a clear indicative of our lower Pannonian geology. And we can see on the next time structure, there is also, we can see the same low impedance features also reforming some kind of fluid field geometry. So based on this discovery, we will run into the same crossplot that we have on the well data. And we achieve this integrated delineation between the SAN 1. So based on this delineation, we can define the prospects of the new location of the hydrocarbon accumulation. The green one is the oil, and the red one is the gas accumulation. So the interesting part is the SAN 1 and SAN 2 is penetrated with the exploration well, which is a confirmed presence. And the SAN 3, we have found new prospects on the top of the structure, which is previously not defined by the previous drilling. So this is the new discovery that we have seen on this study. So coming into our conclusion that the Poisson ratio and the Poisson impedance and length parameter is reliable and advantageous tool for quantitative seismic interpretation, and the prospective sandstone is characterized by low impedance, low to moderate S impedance, low and low Poisson ratio. Mu rho are considerably moderate, and lambda mu rho cutoff, the common cutoff, is a practical way to discriminate between gas, oil, and low or water oil to brine. And then the prospects on SAN 1 are mainly distributed on the northern flank of the anticline, and on SAN 2 and SAN 3 time structure, the prospects are pronounced as a meandering channel geometry extending on the top of anticline. And I also would like to acknowledge Moore Group to providing this study. And this is the reference that I used on the study. And thank you for the attention.
Thank you very much for your presentation, Aka. I might have one quick question, and anyone else, of course, don't hesitate to put your questions in the Q&A or in the chat below. I think I only saw sand and shale in your example. Do you also account for other lithologies, or is the method only applicable on those two?
Okay.
Stuff?
So yes, based on the literature that we have read, it's actually could define coals, carbonates, and also hydrates that you have mentioned. But on our specific location, it's only consisting of shale and sands.
All right, thank you.
Okay, so we can move on to the presentation of Andrea Pavel. The first one, she's from the University of Bucharest, and is showing us today the application of near-surface geophysical methods for the identification of seawater intrusions.
So, hello everyone, my name is Andrea Maria Pavel and I'm an undergraduate geophysics student at the Faculty of Geology and Geophysics, University of Bucharest, Romania. And today I will have two presentations. The first one is about the application of the near-surface geophysical methods for the identification of seawater intrusions. And both of my presentations are realized by me and my professor coordinator, Bogdan Mihai Niculescu from the Department of Geophysics. During the presentation, I will talk about the case study, the purpose of it, the geological setting, information about the geophysical data acquisition, the results we obtain, and final conclusion and references used. So, the case study chosen for this topic is the Vama Veche village from Constanța County, Romania. We performed the measurements in 2019 during the SEG Bucharest Student Chapter Field Camp with a team formed by 2 professor coordinators, 1 team from the Geological Institute of Romania, and 19 students from Romania and Poland. The field camp was based on hydrogeophysical investigation of the environmental hazards from the Romanian Black Sea coastline, and we thank the SEG for the field camp grant as well. In the slides, you can see on the left side the poster of the field camp, and on the right side the group picture with the team from our field camp. The purpose of the study now. Generally speaking, the seawater intrusions represent one of the main causes of coastal freshwater contamination. This phenomenon can happen because of the brackish water of marine origin is moving to the freshwater aquifers, being stimulated by the natural processes or human activities, such as uncontrolled exploitation of freshwater. In our country, on the Romanian Black Sea coastline, were identified the 2 places with seawater intrusions, such as Vama Veche, which is the case study for this topic, and Costinești village, which is close to the Vama Veche village as well. Now I'm going to talk about the geological setting. So the Vama Veche village is located in the southern part of the Romanian Black Sea coastline. With the red square you can see on the map, you can see the study area indicated. And from the geological point of view, the South Dobrogea compartment is a part of the Moesian platforms, and its limits are the Capodava-Ovidiu fault in the north part, the Intramoesian fault in the south part, the Danube fault on the west part, and the compartment continues to the east to the Black Sea continental shelf. Also, the freshwater aquifers, which are topic of this presentation, are hosted in the Sarmatian limestones. On the right side, you can see the structural map of the South Dobrogea compartment and the main fault system. Also, the geological cross-section marked on map I will present to you in the next slide. Here, you can see the geological cross-section I have talked about before, and with the brown star, I approximated the location of the Vama Veche village. The limestones I'm going to talk about are represented by the yellow color, which indicates the Sarmatian and Badenian ages. In this slide, you can see 2 pictures, and both of them are taken from the field campaign. And in the first one, you can see the contact between loess deposits and red shale deposits marked with black arrows. And in the second picture, you can see the cliff outcrop from the Black Sea coastline. Now I will talk about the geophysical data acquisition from the field campaign. So in August 29, we performed the data acquisition on 15 profiles. On the right side of the slide, you can see the localization of the profiles marked on Google Earth. And now I will describe the profiles. With blue color from 1 to 5, there are represented the magnetic grids. With the red lines from 1 to 8 are represented the geoelectrical profiles, and with green color are represented the 2 gravity profiles we performed during the field campaign. In this presentation, I will only talk about the magnetic and geoelectrical data. Now I will talk about the measurements. So the geoelectrical measurements were performed on 8 electrical resistivity tomography profiles, ERT, during the 29th field camp. For these measurements, there were used between 42 and 64 electrodes with 5 meters distance between them. Also, the 5 profiles were done near the coastline, and 3 of them were done across the National Road 49. So 3 profiles near coastline and 2 across the road were done with the north-south orientation, and 2 profiles located near the coastline and 1 across the road were done with the east-west orientation. We have done these arrangements because we wanted to see as many data as we can. So after several tests, the chosen electrode configuration was dipole-dipole. And on the left side of this slide, you can see me and my colleagues listening the indication from the mentor from the Geological Institute of Romania. He explained to us the configuration of the electrodes and how we can set the equipment as well on the field. Now I'm going to talk about the magnetic surveys we have done. So the magnetic surveys were performed with 2 magnetometers. We choose one for the actual measurements on the profiles and another one as a base station. The data acquired from the base station we used to eliminate the diurnal variation effect. So there were some students who performed the measurements on the profiles I showed you before, and a team of students who stay at the base station the whole day to acquire the data for the correction we made before, after the field camp. And to be sure that everything is taken into consideration at the processing and interpreting part, the pipes, high voltage power lines, and metallic objects were pictured and marked on map. And on the right side of the slide, you can see a picture with me doing a magnetic survey, and also you can see the environment, how the environmental looked on that field camp. It was the final week of August, and that's how the vegetation looked. Now I'm going to talk about the results we obtained, some of the results we obtained after this field camp. So on this slide, you can see 2 of our 8 geoelectrical profiles we performed. On the left side, you can see the apparent resistivity pseudo section and the true resistivity one for the profile 5. And from this section, you can see the Sarmatian limestones indicated with arrow, and is represented. They are represented by the values from 70 ohm meters. And the shales and the loess deposit as well indicated with arrows, which are located at the top of the Sarmatian limestones. Also on the right side, you can see the profile number 8, and from the true resistivity pseudo section, you can observe the intrusion I talked about before, which is indicated by the values of 10 ohm meters, and the Sarmatian limestone, which on this profile are closer to the surface, and of course, you can see the shales as well on the right part of the pseudo section. Now, some of the magnetic results. Here you can see the total magnetic field map measured in nanotesla, and which was acquired in the profile M5. And we interpret this perimeter, and we choose this one because we could correlate it with the geoelectrical profile 7 and 8, which were the most suggestive for us. And from this total magnetic field map, you can see on the right side of the map, the shales which are covering the Sarmatian limestones, and represents the lower compartment. And on the left side, you can see the limestones, which represent the upper compartment. These 2 compartments are separated by an interpreted fault, which I indicated with the black line and the letter F. Now, in the end, the conclusions for this case study are based on the correlation of the geophysical data with the cliff outcrops and the data from the contaminated water well drilled near the village. We chose this data as the control data because we wanted to interpret the data we acquired on the field during the field camp, but we wanted as well to have some data to control the interpretation part. The 2D geoelectrical models help us to identify the seawater intrusions, which are represented by the values of between 5 and 10 ohm meters at approximately 45 meters depth. And the magnetic data helped us to interpret the fault and the 2 compartments. That was, these are the references I used for this presentation, and that was my first presentation. Thank you very much for your attention, and if you have any question, feel free to open your microphone or write in the chat box.
Thank you very much for your presentation. So do we have any questions? How do you integrate the data that you have from the electrical surveys with the magnetic one?
You mean in the softwares, or like in a workshop where we combine data? I mean, you mean that if you use some specialized software to integrate it, or just separate?
No, generally.
Oh, okay. So we process and interpret the electrical data separately, the magnetic data processing and interpretation part, and then at the workshop, because after the field camp, we organized the workshop for everyone, we analyzed and correlated the data because the electrical profiles were done almost in the same places where the magnetic grids were placed. And for that reason, we were able to combine the data. If you remember, it was a slide with the electrical profiles after the processing part. And on one electrical profiles, you can see the limestones on the top of the profile. That helped us to better understand the total magnetic field map, because there I showed you the Sarmatian limestones, which represent the upper compartment.
Thank you.
I hope I understand. I explained your.
Yeah. So I don't know if anyone has any. Okay, we have here. Yeah, we have a question from either. Which one gave better results, magnetic or gravimetric in fault determination?
Sorry, can you repeat, please? I'm not able to see the chat. I don't know why it's not opening. Oh.
Which one? Okay, so which one? Okay, I can write it in the chat if it's better. Which one gave better results, magnetic or gravimetric in fault determination?
In our case, we chose the magnetic data because we also performed two gravity profiles, but I did not present to you because the data weren't good. So in this case, we prefer the magnetic data to find the fault.
Yeah, sure.
So yes, hello everyone, I'm Aukje Veldmeijer, and together with Roberto, we chair this last session of today about case studies. And our first speaker is Christian Cervo of the University of Napoli. Christian, go ahead.
Hello everyone. I'm going to share it. Okay, can you see it?
Yes.
Okay, perfect, thank you. Hello everyone, I'm Christian Cervo, and I'm a physics student of the University of Naples, Federico II. I'm also a member of the SEG student chapter, and today I'm going to show you my work about the sedimentary record of Mars, its geology, and its sedimentology of deposits from G0 crater. We all know that Mars is the fourth planet in terms of the distance from the Sun, and it also called the red planet thanks to the presence of iron oxides present on its surface. The first year of exploration were surely the 1960 and the 1970. In fact, in 1964 November, NASA's probe Mariner 4 carried out a flyby all over the planet, capturing numerous images of Mars, of its atmosphere and its characteristics. Let's go on and let's see that also a lot of probes, also landers and also rovers landed on the planet. In fact, the last one to arrive is Perseverance rover that landed in the 18th of February in 2021. Let's talk about the main characteristics of Mars. First of all, we have its crustal dichotomy, where here there is geological eras and also is magnetic field. About this crustal dichotomy, that is the division between the northern hemisphere and the southern hemisphere, we can see that the northern hemisphere is void of crater. That's an indicator of probably over there was an ancient northern ocean. Instead, in the southern hemisphere, we have a lot of craters like the Hellas Planitia Basin, which is the topographic low on Mars surface. And over there on the left, we have Tarsis volcanic region, where the Olympus Mount, that is the highest volcano in the world solar system is 25 kilometers away, resides. Moreover, here we have a global geological map with 3 colors that are indicating us the geological time scale of the planet. Here we have the first one up to 4,300 billion years ago. That is the Notian era. That was a period in which we can see an aqueous alteration to natural pH, and also there was the period where the first clay mineral formed. Moreover, we have the Hesperian period where the first sulfates form, and up to the present era, we have the Amazonian era, which is the last one up to the present era, as I said before, where the first iron oxides formed. Over here in figure C, we have the magnetic field. The magnetic field is an ancient one. It probably goes back to the Notian era, and it's a radial magnetic field. In fact, we have this data thanks to the data collected by the CRISP spectrometer, thanks to the presence of the ferric minerals present on the surface. In fact, here we see all the anomalies of magnetic anomalies. Okay, Mars has a lot of differences and similarities with the planet Earth. Let's see one of the most important morphology on the planet. I'm talking about Valles Marineris. Valles Marineris is a canyon system. It was formed in a relaxed regime. In fact, as we can see, is 4,000 kilometers long. In fact, it's like the length from the west coast of the United States to the east coast of the United States, 200 kilometers wide and 7 kilometers deep. The Valles Marineris has a lot of distinctive structure, as we can see in figure B, C, D, also compressive structure, like in figure E. Here we have the distinctive structure, the compressive structure, sorry, where the ILD resides. What about the ILD? ILD are, we mean interior layer deposits. They are very stratified deposit layers, but whose origin is still debated. Moreover, we can see a lot of tectonic structures like faults in figure C, like erosional structure, maybe probably shaped by erosional processes, exogenous processes shaped by wind or river erosion, or also structural one, like here we have a close-up of layers in the metastrasma in figure B. Why is G0 crater so important? Thanks to the analysis of a perseverance rover that have been performed during these years, we have a lot of knowledge of its analysis and this deep study on the crater. The G0 crater has been studied from the rover Perseverance because we want to understand whether or not it was adult-like deposits, and we can do this through its mineralogy and through its sedimentary structure present in it. As we can see, in fact, we have 2 inlet valleys and 1 outlet valley. Here we have an enlargement, figure B, of the western far of the G0 crater, because we have 2 fan. One western fan over here and another northern fan here. So we can find these 2 fan in correspondence of the 2 inlet valley. As said before, here we have the digital elevation model of the enlargement of the figure B. That is the overview of the western fan shaped deposit of G0 crater. Now, as I said before, very important things are the mineralogy and the structures, geological structure present in it. So now let's focus on the mineralogy of the western far in G0 crater. As we can see in different colors, we have various minerals, such as here in the prior part of the western far, we can find the carbonate-rich magnesium in yellow, the prior part, and here we have an enlargement that the carbonate-rich magnesium can be found in correspondence of the point bar. So that is an indicator that we can find that this can be found in a type deposit. Moreover, we have in blue the smectite rich in iron and magnesium in the distal parts, and eventually we have the olivine sand over here shown in red. That is a sand olivine, so volcanic, and that is such another indicator of the type deposit. Here we have in figure C an enlargement of the smectite rich in iron and magnesium. Here in figure B, we have the crease, so the spectrometer that I was talking about before, of the spectra of carbonate of rich in magnesium and the iron, and also the smectite. Smectite was indicated like S1, S2, or S3. Perfect. Was it an ancient lake? The answer is yes, it was, because as we can see here, we have in blue, we have blue shading that indicated a Sumeru lake level filled to the 2,490 meters here in gray colored. The red star indicate the landing site of Perseverance rover, just over the Kodiak that I'm talking about just later. And we can see also the northern fan and the western far. And the rocks present on the crater floor might not have been in place during the period of lake activity. So both fan are above the infrared lake levels and surface. And the black line outdoor imply the minimum water stand. So we can affirm that yes, it was an ancient lake. So currently it's a paleo lake over there. Let's focus let's focus on the battery Kodiak. That is a sedimentary structure be found thanks to the photo camera present on the Perseverance rover that was situated just 2 kilometers from it in Octavia Battery, as I said in the previous slide. And we can see here that is such a pretty similar structure like we have on the planet Earth. In fact, here we have like a structure like a hill with a top flat, fairly slippery slopes, and also we can focus on the east strata. So we can see here K1 is the larger one, is the higher one with the 17 meters of height. Or more, or above it, we have K2, the less high than K1, with an inclination of 35 degrees. And here we have enlargement, and we can see the three structures that are typical of sedimentary pattern. So we can see, like, for example, the bottom set, the first set, and the top set. Here, the bottom set that are the parallel to the base of the structure. First set, they are the steepy one, the steepy slope one. And above it, we have the top set. They are the sub-parallel layer. Let's going on, and let's focus on the figure F. That is an enlargement of the outcrop shown here of the wall structure. I mean the butt Kodiak. Okay, as we can see in the focus enlargement, we have the truncation between the top set and the foreset. As we can see, there are also couples, so there are a lot of indicators that we finally find ourselves in the type deposits. So thanks to the mineralogy that we have found at the western front of G0 crater, and thanks also to the deposit and also this sedimentary structure found in it, we can finally confirm that we are in the type deposits, and we have deepened our knowledge of this planet, and let's hope to continue in this way. That's all for me from my part, and thank you for your attention.
Okay, thank you very much, Christian, and thank you for being this time.
Yeah.
I'd like to give some space to any question from the audience, if there is any. Otherwise, I have a question for you.
Yep.
I'd like to know what is the resolution of this analysis. What is the maximum resolution that you can reach?
Yeah,
from spectral analysis.
Okay, yeah, we have here the spectrometer analysis. Okay, here, for example, over here. So thanks to the CRISP spectrometer, we have like such a high resolution because thanks to the satellite that we have used, we have the CRISP that is one of the best to get a higher resolution, and also the HARISE one. It's one of the most important satellites that are studying this moment all the topography, but also the atmosphere of the red planet.
Just in case, okay, I'd like to ask you another thing. Do you know if any similar work were done in other places, nearby areas to this place? And do you, in this case, is it possible to correlate the sediments that you have identified in the span with formations that are close by? Like,
yeah,
I mean, in terms of sediment transportation.
Yeah, sure. Yeah, a lot of studies have been performed during this year, not only with Perseverance rover, but also with the Curiosity rover, InSight rover. In fact, we have like also geophysical studies to get information about the Earth space. But of course, also with the InSight mission, we have been performing a lot of information about other sedimentary structure next to the G0 crater. Because here next to where the Valles Marineris is, where we are capable to find other structure like this. So yes, we have a lot of information of the sedimentary and sedimentology of the planet.
Okay, thank you very much.
You're welcome. Thank you.
Okay, I think we can move on. We are perfectly in time.
Okay, thank you.
Yes, thank you, Christian, for your presentation. Our next speaker is Pascal Rousseau, also from the University of Napoli.
Hi, I'm going to share the screen. Okay, I hope you can see it.
Yes, we can see it.
Okay, hi everyone, I'm Pasquale Russo and I'm geophysics student from the University of Naples, Federico II. I'm also a member of the student chapter of Naples, and today I present you my dissertation work about the measurement of the vertical gradient of the total field that I made with the FAM magnetometer in the area of Presenzano in southern Italy. The aim of this study was to test for the first time the FAM magnetometer in a vertical configuration and compare the result with the measurement of the total magnetic field. In this study, we used the geometric FAM magnetometer in the development kit version, as shown here. And this allowed us to change the configuration of the magnetometer and test a vertical gradiometer spacing the two sensors of 25 centimeters on the vertical axis using this polystyrene support. The great advantages of a FAM magnetometer are its lightweight, less than 1.5 kilograms, and its very high sampling frequencies of 1000 Hertz. So survey line with great resolution can be obtained, and then you can sample magnetic noise due to nearby power lines at a frequency of 50 Hertz, thus allowing efficient filtering operation. We conducted two different surveys. The first one was over known magnetic targets, which allowed us to have a forced test in uncontrolled environment, so that we could then carry out a survey in a real geological situation. The first test was carried out on the Monte Sant'Angelo campus in the University of Naples, with the aim of detecting the magnetic anomalies generated by known object placed in a known position in the survey area, ferrous object. We made the measurement of an area of 10 for 10 square meters with a spacing between the profile of 50 centimeters. So observing the total field map and the vertical gradient map, both from the unfiltered data, it's clear that it's easier to identify the two metallic sources on the gradient map. Indeed, the gradient allows us to focus better on the two metallic sources. In addition to the two metallic sources, there is also a third sources in the top left corner, maybe generated by some metallic object buried in the survey area. Observing the profile placed at x equal 1.5 meters, this one, for the total field and the vertical gradient, again, both are unfiltered. Looking at the noise signal ratio, we can see that for the total field is greater than for the vertical gradient. So this confirmed the ability of the gradient to remove time varying signal, like variation of anthropic origin due to nearby power lines, whose signal is well sampled by the FAM magnetometer. Finally, looking at the total field map, there are oscillations along the direction of the profile, which are absent from the vertical gradient map. In fact, the measured total field shows significant fluctuation due to the different local magnetic field sources, superimposed by an intense high frequency signal related to the presence of the nearby 50 Hz power lines. It's a well-characterized noise, which can be removed relatively easily with the low-pass filter in the time domain. In order to choose the right cutoff frequencies, we obtain a frequency spectrum and found that is dominated by the low frequencies, and that the noise level is reached from a frequency of 13.3 Hz that we chose as the cutoff frequency. So the total field map and the vertical gradient from filtered data are obtained. So looking at the total field map, the oscillatory pattern present in the previous map from the unfiltered data is now removed. While looking at the vertical gradient map, it does not change too much. If we switch between the slide. So this is due to the automatic removal of most of the time varying signal obtained by the gradient. Indeed, the 50 Hz noise is greatly reduced by the vertical gradient. A second test was conducted in the quarry area of Taverna San Felice in Presenzano with the aim of detecting magnetic anomalies generated by surface geological target. In particular, the quarry is located at the base of the southwest slope of the Cesima mountain, which is used for the extraction of limestone for concrete purposes. The only case in Europe of a Pleistocene magmatic dike embedded in a sedimentary rock emerged along the quarry face. So in order to investigate the horizontal extension of the magmatic rocks in this area, we carried out 5 measurement profiles. 3 profiles were made above 3 quarry steps, the excavation of which brought to the surface a portion of the dike. In this picture, I'm showing for each profile at the top the total field anomaly and at the bottom the vertical gradient anomaly. So looking at the anomalies, there is a good spatial correlation between the 3 profiles, with the maximum values of the anomalies all concentrated in the southeast portion of the profiles here. This could be a clue to the presence of the igneous body in this area, consistent with the fact that the dike is visible in outcrop in the same area here. The vertical gradient anomalies along the profile AQ0, this one, also have lower amplitude than the other profiles in the southeast portion here, which could suggest that the igneous body tends to deepen in this point. So the gradient allows us to have more detailed information on the position of the surface sources, narrowing the area of the anomaly linked to them, which allow us to distinguish the area of dike outcrop. So I put this black dotted line to separate the area where the dike is in outcrop or near to the surface on the right of this black dotted line. The profile AQ3 is located at an higher elevation than the others and extends along the southwest side of Cesima mountain. In this area, outcrops of lavas and slag can be seen, which end laterally on the carbonate rocks of the relief. So observing the anomaly generated by the total field, this blue one, we can see that the red arrow indicates the discontact on the profile, where the anomalies decrease instantly. So we can say that here we have on the left of this red arrow a work made by igneous rock, and on the right a work made by limestone. Observing now the anomaly produced by the gradient, the orange one, the greater detail allows us to distinguish the cropping point of the igneous rock with greater precision, identifying, for example, in this section, a point where the anomalies decrease. So maybe here the igneous rock are deeper. So in conclusion, FAM gradient measurement detect shallow sources with better resolution than the total field measurement. It's also able to automatically remove time varying signal, such as the power lines noise at 50 Hertz. So FAM gradiometric setup could be useful in many contexts, such as archaeology, quarry environment, civil engineer. And finally, FAM gradiometric system could be used for UAV drone surveys, where the FAM magnetometer is carried by a UAV platform. So finally, this work makes us able to plan a drone-borne survey in the same area. It will cover all the impervious quarry area to quickly mapping the whole igneous body. Thanks for your attention.
Thank you, Pascal.
You're welcome.
There was a question in the chat for you. Why is the dipole of S1, so circulating 1, I guess, has east-west direction, whereas S2 has north-south direction? Aren't they on the same polarization direction?
Is in the chat the question?
Yes, it's on in the chat.
Okay, so just a moment. I'll take the. I don't know how to see the chat to answer the question.
It should be. You should be able to see it in the lower bar, but I can send it to you.
Okay, thank you. Why the default S1 direction?
Can you see it?
Yeah. Okay. So I think it is talking about this survey. Yeah, so the dipole have the same direction. So I'm not sure about the question. I think I answered it.
Okay, maybe you can leave your contact. You can, of course, continue the chat.
Of course.
We also have a comment. I don't know if it's a question or not, but either is saying that the meter is also useful for fault detection.
Yeah. In fact, when I started this work, my intention was to find a great fault present here above the query steps, but was so difficult to go in this area because it was so dangerous walking this area. So maybe in the future, with the help of a drone platform, we will able to test if this method could be used also for the detection of a fault. But now we don't know because we haven't tried it.
Okay. Thank you very much, Pasquale, for your interesting presentation, and sorry for the inconvenience.
No, don't worry.
Okay, we can move on to our last speaker of today. Andrea will present her second presentation of today.
Thank you. Can you please confirm me that the presentation is in the presentation mode? And you can hear me well?
Yes, I can hear you well.
Now I can start. Hello again. For those who did not attend my first presentation, my name is Andrea Maria Pavel, and I'm an undergraduate geophysics student at the Faculty of Geology and Geophysics from Romania. And this presentation will be about the archaeological geophysical surveys applied in ancient Roman town Romula from the old county Romania. And both of my today's presentation I realized with the help from my professor coordinator Bogdan Mihai Niculescu from the Department of Geophysics. The topics I'm going to talk about are the presentation of the case study, the purpose of it, the localization of it, the historical context, information about the geophysical data acquisitions, results we obtain, conclusions, and references used for this presentation. So, the case study chosen for this topic is the ancient Roman town Romula from the old county Romania, and we performed the measurement in 2020 during the SEG Bucharest Student Chapter Field Camp with a team formed by 2 professor coordinators, 1 archaeologist, 1 team from the Geological Institute of Romania, and 12 students from the University of Bucharest. The field camp was based on archaeological geophysics for sustainable local community development ancient Roman town Romula, and with this occasion we thank SEG for the field camp grant again. And in the slide you can see the poster of the field camp and the picture with some of the students who attended the field camp, and also the excavations from the past field campaigns. Now the purpose of the study. As the main purpose of this project, we want to identify the walls and the houses from the ancient Roman town Romula. And for this study, we applied multiple methods such as geoelectrical, magnetic, gravity, and topographic methods. Our field camp has also a social impact represented by the sustainable local community development, because our purpose was to include the Romula archaeological site in the list of UNESCO World Heritage Sites. Also, during the field camp, and not only, the students had the opportunity to learn and apply multiple geophysical methods for archaeological purposes. Now I'm going to talk about the localization of the case study. The archaeological site Romula is located in Reșca village, Old Country from Romania, at approximately 160 kilometers from Bucharest. From the geological context, the Romula site is located in the Wallachian compartment of the Moesian platform, and the compartment is delimited by the Pericarpathian fault in the north side, the Intramoesian fault in the east side, and the Danube River on the south side. These are the limits from the Romanian territory. Also, the geological formations from the Romula site are represented by the leftoise deposits, shells, sands, and gravels from middle and late Pleistocene. In the right side of the slide, you can see 2 maps which indicated the location of the Reșca village and the Romula archaeological site near the Reșca village. Why the Romula site? because the Romula was the largest economic and cultural center in this area, and the fortification was built in the Emperor Trajan period during the first war between Romans and Dacians in 101, between 101 and 102 Anno Domini. The central fort has a wall with the width of 1.90 meters and the foundation at 4.50 meters under the today's soil level. Also, on the right side of the slide, you can see the Roman Dacia map, and with the brown star, I indicated the Roman town. Now I'm going to talk about the geophysical data acquisition from the field campaign. In September 2020, we performed the data acquisition of 14 grids, or 14 profiles, and from M1 to M3, there are represented the free magnetic grids, and from the I1 to I7 are represented the geoelectrical profiles, and from G1 to G4 are represented the gravity profiles. In this presentation, I will talk about only the magnetic and the electrical data. Now I'm going to talk about the measurement, the extra measurement. So the magnetic surveys were performed with two magnetometers. We choose one, the cesium vapor magnetometer with an integrated GPS for the actual measurements on the profiles, and another one proton precession magnetometer as a base station. The data acquired from the base station we used to eliminate the diurnal variation effect. And again, as I said in my past presentation, a team were on the field to do the measurements on the profile, and some students were at the base station to acquire the data for the diurnal variation effect to be eliminated. And to be sure that everything is taken into consideration at the processing and interpreting part, the high voltage power lines, metallic objects, and wire fences were pictured and marked on map. In this slide, you can see a map with the perimeter one, where the perimeter one, where we performed the magnetic measurements and at 2 meter spacing between the profiles. And on the right side, you can see a picture with me doing a magnetic survey. Now I'm going to talk about the geoelectrical measurements. So they were performed on 7 electrical resistivity tomography, ERT profiles during the 2020 field camp. And for the measurements, there were used 64 electrodes with 1 meter distance between them. Also, the first 6 profiles were done with the northeast and southwest orientation, and the last one with the northwest-southeast orientation. The lengths of the geoelectrical profiles were between 50 and 190 meters, depends on the places where they were settled, because the perimeter wasn't in the square form. And after several tests, the chosen electrode configuration was dipole-dipole. Also, on the right side of the slide, you can see a picture with the geoelectrical measurements during the 2020 field camp, and also you can analyze the environment. Now, I will talk about some of the results we obtained during the field camp. And here you can see a magnetic anomaly map we obtained after data processing for the perimeter one. I marked on the map some of the anomalous zones, which can be interpreted and take them into consideration. So the first zone is a northwest-southwest lineament, which can correspond with a northern brick wall. Also, this wall can be in the continuation of a brick wall discovered in the archaeological excavation campaign in 2014. The second zone is the largest one and can be interpreted as the possible main build area. The first zone can be associated with the trench from the archaeological excavation campaign, which took place between 2014 and 2018. On the fourth zone, you can see a northwest-southwest lineament, which can also represent a brick wall, a small brick wall. And the last one, zone number 5, can be interpreted as a zone with artifacts because of the high values of 150, 200 nanotesla. On this slide, you can see some of the geoelectrical results. On the left side is the electrical resistivity tomography profile number 2, which was processed in the RES2DINF software. And from the true resistivity pseudo section, it can be interpreted at the depth of approximately 2 meters with values higher than 400 ohm meters. The northern wall indicated as well on the magnetic map I showed you before. From the second picture on the right side, you can see some of the geoelectrical profiles represented in correlation with the satellite map of the area for a better visualization of the data. Now I will say the conclusions, some of the conclusions of our project. So the anomalous zone or lineaments indicated on the geophysical data can be represented by the boreal structure from the fortification. Also, the majority of the structure are located at approximately 2 meters depth. The baked bricks and brick wall can be correlated with the anomalies higher than 80 nanotesla, and the geoelectrical measurements showed us the isolated structure with values higher than 300 odd meters, which can suggest the structure from the fortification. And as a proof of our great work during the field camp and the high quality of the data, in 2021, there was another archaeological excavation campaign where they discovered structures from the fortification and ceramic pots. The structures they discovered are correlated with the anomalous zones we identified. Here are the references I used for this presentation. And thank you very much for your attention. If you have any questions, do not hesitate to contact me. And this was the last presentation for the SEG European and Eurasia Virtual Student Conference. I want to congratulate everyone for their effort to make this conference happen, and I hope to see each other at online or in-person events soon. In the end, I would like to recommend to everyone to take part into field camps, because these two presentations I had today were based on 2 of more field camps I had the opportunity to attend and organize. Even if I was in the first and second year of studies when I attended the field camps, and to be honest, I did not understand too much at the moment, I'm glad to say that after these years, I'm able to share with you the technical details. And I can say, even if you believe that the topic from the field camp is too complex for you on that moment, I can recommend you to just take the opportunity and participate in. Maybe the activity will not help you so much on that moment, but will definitely help you in your future career. And also participating in all SEG field camps if you can. Thanks for your attention.
Thank you very much. It was a very nice presentation. And yes, it's true, getting involved in the field camp is always super useful all the time. Okay, we have 3 questions from the audience. So the first question is, what is the raw material of the archaeological features?
Like the geological formation, or that's what you want to know? Because we had the brick walls and the ceramic pots. You want to know from what is the raw material for the brick wall?
I believe so. But
okay, yeah. It's a combination between shale and loess.
Okay, the second question is, the gradient mode in magnetometers is useful in subsurface detection without needing to base station.
The question, or
it's the second question. Is
we wanted to have a base station because we wanted to be sure that we eliminate every diurnal effect, and because our focus was on the very close to the surface. We wanted to acquire data at the near surface, so at maximum 2 or 3 meters. So that's why we wanted to eliminate every data we don't want to include in our processing and interpreting part. That's why we also marked everything we found on the field which are not related to real anomalies.
Okay. Like the third question, very quickly. There are many monopoles in the map. Could you explain what they are?
It was like a fortification, so most of them are related to the ancient town. So we found houses, brick walls, ceramic pots. So it depends if the anomalies are on the large place, then can be interpreted as a brick wall, or if it's something really, really small, maybe it's not a brick wall, it's just something related to the to something from the house.
Okay. Last question is either is asking why did you use the gradient mode? Why didn't you use the gradient mode instead of the normal measure?
To be honest, it was a field camp and we wanted to everyone
okay,
to
yeah.
to apply the methods, to understand them, and to apply as many methods as they can. So after that, we also had the workshop. We explained the details, and also we have talkings about these topics as well. So it was maybe we did not choose the best option, but it was the best option for us to teach the students as well, because I did not understand very well the information when I was in the second year too. So now I'm able to explain to you because I attend the field camp, and that's how you can learn from experience on the field. And you can learn from your mistakes as well.
That's true. Thank you. Thank you very much. Thank you, everyone.
Thank you very much.
I think we can close this session. We can now move on to our evaluation of the presentations, and we will back to you in 5 minutes, I think.
Yeah, so maybe just to interrupt there real quick, Roberto, while we do the evaluation, I think maybe Andrea, it would be nice if you can go into a little bit more detail on how you can set up such a field work with SEG. I think you already did a great job of advertising it, but it might be nice, for example, imagine that there are some SEG students here with that chapter that are thinking of setting up such a field camp. Could you maybe elaborate a little bit more on how you advise them on going about it, how to plan this stuff? And then if you can keep them busy for a little while, we can come back to you with all the scores in just a minute. So thank you once again for your presentation as well.
Sure. It is possible to make everyone panelists just to open their mic and have a free discussion, or based on
surely
questions?
Yes. Yeah. Okay,
you don't want, it's not a problem. So do you have any questions related to the organize of a field camp, or I just summarize how you can write the project, the ideas, and how to organize it after you receive the accept?
I got a question, or how did you came up with the idea of this archaeological site or something, or do you like archaeology, or is there
I like archaeology
reason?
and the identification of seawater intrusions as well. Okay. So most of the times when you choose the subject of a field camp, as in our faculty, we choose something like for what we have data from the past times. And for both of my study I presented you today, we have some data from the field measurements. They have been taken like 10 years ago or something like that. And because it's a field camp for students, we want to have like this type of data from the past to correlate with the actual data, because we want to show to them what they are going to do, what they should expect, and to analyze, to correlate the data. So if you have some data from from 10 years ago, and you have some data from the past week, you should be able to correlate it to see what we have done better now, or why what they did 10 years ago was better. So that's why we choose this type of topics. And for the archaeological field camp, we wanted to do something different. And because we don't have the geophysical field camps for archaeological purposes every year, it was the first one, as I remember. Yeah, we chose this topic because we also had that brick walls they discovered in the past. We have some true data, like we know that we will find something there, and it was easier for us to explain to the students. I'm talking like I explained to the students, but I was one of them who did not know something, but I organized it well. So yeah, we believe in this type of things. We train students from the first year to be able to organize the field camp, even if they don't understand the topic of the field camp, because in the future they will, when they will be in the final year, they will be ready to for the organizational stuff, which are not related to the technical topic of the field camp, but also be ready to explain why we applied something in a field camp. And we also had an archaeologist who helped us, and it was really nice to be on the field to apply geophysical methods and on the on a break, he explained to us about Roman Empire and why we are on that place on that moment.
And they're probably pretty happy to get this geophysical information, right? So do they actually use it to dig somewhere, or?
Yes, they used the geophysical information the last year when they did that excavation program, because they did the excavation on our anomalous zone indicated on the map. So that's why I saw like we have facts. We saw picture with the brick walls, where they excavate from the anomalous zone we indicated. So it's nice when you are a student and you participate in this type of field camp, and after a year or two, you see that someone came with results based on your work, and you can also use the results for bachelor thesis, dissertation, PhD, and we also have students who are doing this in the present. So yeah, we like this.
At my university, I made a lot of field trips organized by my university, just not by SEG or anything. But you organize it every year, or?
We are trying. We have field camp grants, almost every year. But if we not have a grant, we are trying to find the funding from some companies. So we are trying to organize it every year because it became a tradition, and we don't want to disappoint students. Like when you are in a second or third year or even final year, and you want to promote the chapter to the first year students, and you tell them that every year you organize a field camp and the next year you don't have a field camp grant for them as well, you should do something to involve them as well in another field camp, because after that, if you don't do a field camp, maybe they will lose their interest for the SEG. So we should do every year, even if we should work more.
Sounds reasonable. Do you have already an idea for next year, or?
For the summer or for the
for the next time? I don't know when it's going to be the next time.
Yes, for 2 field camps actually. We will come back to find the seawater intrusion in the Costinești village, which is closer to Mangalia village, which is closer to Vama Veche. We want to see the seawater intrusion between the Costinești and the Vama Veche villages, where already found the seawater intrusions. And we also want to identify the landslide and the cause of it from a place near Bucharest. So we want to do 2 field camps where we will involve students from each year of studies. So we are busy this summer.
I see that Laurie also shared the SEG link for any student chapters that might be interested in chat, so there you can find out more. I think we are ready, so thank you, Andrea, again for covering our time, and I think I can give the word to Denise now.
Yeah, thank you. If there are no further questions, then we can wrap up the program. First of all, we want to thank you all of the students who did make presentation. Each of you have a great presentation. Personally, I learned new insights today, and I hope everyone has a good feedback. Also, I would like to add that for the networking, I'm inviting you all who wants to stay. Further, thank you all of the audience for joining. I hope we can meet at the next virtual conference events as well. Maybe next time you will be the person who will make the presentation and gives us different understanding on your research area. Additionally, I want to mention that again, as Laurie did at the beginning, the 7th Virtual Student Conference will take place on November 2022. So you are very welcome to submit an abstract. Last but not least, I would like to thank all of the chairs of the sessions and Region Advisory Committee and advisors for all of the dedication and hard work they put this event to make happen. The members of the technical committee voted on the 9 presentations. Now I am going to say it. 3rd place is belonged to Andre Pavel from University of Bucharest with the presentation of Archaeological Geophysical Surveys applied in ancient Roman town Romula, Old County, Romania. Second place is belonged to the Marta Faber from University of Edinburgh, 3D imaging of the near surface zone with seismic wave field gradiometry. And first place is belonged to the Wouter Dillenschneider from KU Leuven with the presentation of tuning the sharpness of hydrogeophysical immersion models. Once again, congratulations to all of you who did the presentation. Also, thank you to everyone who participated. We are very pleased with the way the conference went. All of you are very welcome to present and attend as an audience next time as well. Have a nice afternoon, everyone. Thank you.
Yes, thank you all for joining the conference, and hopefully we'll see you again in half a year. Bye-bye.
Bye, thank you.
Bye, thank you.
Bye. Thank you.
Thank you.
Goodbye. Thank you.
Bye-bye.
Bye, everyone.